How to use the Stitching Calibrator for video panoramic calibration. Hi everyone! In this tutorial, we will learn how to calibrate the stitching parameters for panoramic video footage in RidgeRun Stitcher Calibrator. If you're planning to use RidgeRun Stitcher to create panoramas or mosaics from a group of images or videos taken from different perspectives of a scene, then this is the right video for you, so stick around. Alright, let's get started in RidgeRun Stitcher Calibrator. Now, click Panoramic Calibration. Remember, the idea behind calibration is to obtain the right parameters to stitch together the images for a specific setup. The first thing we need to do is to prepare a directory with the sample images to calibrate. Following the calibrator requires structure. We need a project directory with a sample folder for each one of the cameras. That should always be numbered from 0 to the number of images to stitch in the panorama -1. Each folder contains the corresponding sample images. In this first example, we're going to use a 3-image setup distributed horizontally. We're going to select the center picture as a reference, meaning this image will not be transformed and the other two will be wrapped to match the features in the centerpiece. So in our project directory, we need 3 folders called 0, 1, and 2. The folder 0 will always be reference, so the center image will be placed in folder 0, and the left and right pictures in folders 1 and 2 respectively. Please bear in mind that the order in which you put the images in the folders will be the order in which they will be presented in the calibrator to match them. Let's go back to the Stitching Calibrator and load the sample images. Go to File, Open, select the project directory and click Open. The first pair of sample images is shown in the camera's window. We have the center and left images. Now, as we know, the purpose of the calibration is to find the transformation parameters to adjust the target images to the reference. With this tool, you have 2 options to find these values: automatic homography calculation, using the Find Homography button here, or manually adjusting the parameters using these manual edit controls down here. Let's start with the automatic calibration. First, in the overlap window, we need to indicate the overlap region between these 2 images. So let's click and drag the left image to the left side of the window. Notice that when you're holding the click, the top image becomes a little transparent, so you can better adjust the overlap. The algorithm will look for matching features only in the overlap selected area. If you don't have an overlap region, when clicking the Find Homography button, you will get an error indicating that pictures must be overlapped because there is no area for matches to be found. Moving the images to match approximately will help the algorithm find better matches faster. However, if you want, you can set a full image overlap, forcing the algorithm to find matches over the whole images. However, this may lead to errors when other regions have similar features. Once you're satisfied with your overlap region, you can click the Find Homography button to start the automatic calculation of the transformation parameters. This may take a few seconds. You will see the button highlighted until the calculation is complete. Once finished, the stitching of both images is displayed on the homography window. This application offers 2 controls to adjust the automatic homography calculation: the reprojection error and the sigma. Let's focus on the reprojection error first. So, having a pair of points of a reference feature point and the corresponding target feature point projected using initial estimated homography, the reprojection error indicates the maximum distance in pixels for this pair of points to be considered as an inlier. Only inliers are used to refine further the homography calculation. You can change the reprojection error between 1 and 10 pixels, and the best value will depend on your input image sizes and the feature points detected. We can check some of the effects of changing the reprojection error in our example here. Let's just adjust the homography window and zoom in a little bit. This is the result of a reprojection error of 4, which is the default value. Let's now compare the results using a bigger reprojection error, meaning allowing a bigger distance between our points and probably allowing more points to be considered in the homography refinement. Set the reprojection error to 10 in this one, click Find Homography button, and here we go. You can see that for this region, in the floor, the homography calculated with a reprojection error of 10 does a better job aligning this line. Also, if we zoom into the plan over there, you can see how it is better adjusted with a value of 10. As well, the stairs back there look better aligned. So, for this particular example, A bigger reprojection error allowed the algorithm to use some points in the floor area for better adjustment, but there may be other cases where the points are real outliers and will affect a good homography calculation. Okay, now let's look at the sigma control. Sigma is used for the preprocessing to reduce the image noise. Reducing the image noise allows the algorithm to find better feature points. Big values reduce the noise but also image details, whereas small values remove less noise but preserve image details. Bear in mind that your image may not need any denoise at all to work properly in the first place. This will depend on each specific case. Moving forward to the manual edit controls, you can use them to refine the automatic homography results. For example, you can see this tree over here is still misaligned. You can try to adjust the controls to make them match better. Although you can start the image alignment from scratch, we recommend that you use automatic homography detection first and then manual refinement. But to clearly showcase the functionality of the manual controls, let's restart the homography by clicking the button down in the control panel. The application pops up a message window asking if you are sure to restore the homography. This is because you will lose everything we've done so far. At this point we're sure, so click yes, and now everything in the workspace goes back to the default. Inspecting the manual controls, you will see that there are controls for rotation, translation, scale, and shear. To change any of the values, you just need to click on it, and then change the value by clicking the arrows up and down, writing directly the value that you want, or with the up and down arrows on your keyboard. The stitch image with the current homography configuration will be displayed in the homography window. Adjust the homography window to have a better view of the stitching. Currently, the images are overlapping, so the first thing you'll need to do is to translate the target image to one side to be able to see both images. Remember that only the target image is affected by the controls. Set the translation X to a positive value to move it to the right, or a negative value to move it to the left. We set it to 2000 to be a little bit bigger than the image width, so we can clearly see both images side by side. You can use the translation Y to move the image vertically. A negative value will move it up and a positive value will move it down. Use the rotation controls to rotate the image. In X, pitch angle, the image plane will rotate over the horizontal axis in the center of the image. You can imagine it as taking the side of the image and turning. For the Y rotation, roll angle, the image plane will rotate over the vertical axis in the center of the image. This is like taking the image from the top and turning it. Finally, the Z rotation will rotate over the optical axis coming out of the plane. Continuing with the scale controls, they will scale the image width by the factor x and the image height by the factor y. You can make it bigger with number greater than 1 or smaller with a number less than 1. The last control, shear, skews the image over the vertical or horizontal axis. For x, it'll shear the image horizontally by the given angle, using the top left point as a reference, and for y, it'll shear the image vertically using the same reference point. Now that you know the available manual controls, let's try to refine the automatic homography. So reset to go back to default and find the automatic homography. To inspect the results, zoom in and toggle the transparency checkbox. There you can see the change between the target transformed image on the left and the mixed images with transparency applied in the overlap region. You can identify that some regions are still moving and try to adjust them. For example, let's focus on this tree and use the controls to adjust it a little bit better. Toggling the transparency, we notice the tree in the reference to the image is a bit to the left. So the first thought is to use translation to move the target to the left. However, this change will misalign other parts of the image. You may need to take a closer look at the required motion and probably will need to use more controls to get better results. We can try a little bit of shear, and maybe a bit of rotation in Y. C to align these steps back. Now, the tree looks better and the other regions look pretty good. Although the plan goes a little bit blurry, but we're okay with that. Moving on, we need to stitch the following image. So click on the next button. The desert ride JPEG is displayed on the camera's window and in the overlap window. Notice that the stitch result of the previous step is now our reference image. It is a single image instead of two, and we need to define the overlap area between this image and the desert ride image. Select and drag the right image, move it to the right, finding the right overlap between them. Once satisfied, configure the automatic homography and click Find Homography. Check the result. If you want to refine it, you can use the manual controls as we did before. However, for this tutorial, we're going to keep this result as is. So let's save it. Go to File, Save, and save to panoramic.json. Let's go and inspect the file. It is a JSON with an array of homographies. The array contains an object per each pair of stitched images. Each object in the array contains the information of the images, the index of the target and the index of the reference, that will always be 0, and the homography matrix itself, reference to the image 0. You can use this file directly with the RidgeRun Stitcher to create your stitch panorama. Let's continue with a more complex mosaic example. We're going to learn how to calibrate a 6-camera system from start to finish. The footage we're going to stitch is for the custom camera array that has 2 rows of cameras with rectilinear lenses. Essentially, we have 6 recordings with an overlap region between the contiguous cameras. As you know, the first thing we need to do is to prepare the samples directory. We need to get sample frames for each video and place them using the Stitcher Calibrator required folder structure. In this case, we will need 6 folders named from 0 to 5, and we will place the sample images for each camera in the corresponding folder. We will select the samples of the 4th camera as a reference and place them in the folder 0. The following folders correspond in order to camera 3, 0, 1, 2, and finally camera 5. Go to the Stitcher Calibrator and open the Prepare Example directory. The tools load the first sample for camera 4 and camera 3. Let's find by clicking on the Next Sample button a suitable sample with the interesting object in the overlap region that will help us better align the cameras. Here, for example, this car in the middle looks pretty good. We'll keep a full overlap region and start the automatic homography calculation. Check the stitching results by zoom in and toggle the transparency. The alignment looks good, so let's continue with the next camera. The next camera, camera 0, is displaying the camera's window, and the first sample for each of the cameras is loaded. We need to find the same sample we chose before to keep synchrony. Great, we are in sample 6. Now we need to adjust the overlap region, moving the camera 0 sample to the top, overlapping the building. Then click Find Homography. Toggle the transparency to see how well the new stitching looks. It seems to be misaligned around here, so we're going to restart this homography calculation and set a very overlap region. Notice that when we restart, the tool reloads sample 0, so we need to look for our sample again. Set the overlap region more carefully and click Find Homography. Checking the stitched image, it looks better aligned now. Since we're satisfied with the result, let's continue clicking Next. The camera 1 is added to the camera's window, again starting sample 0, so we need to look for sample 6. Here we are. On the overlap window, move the camera 1 sample to the top left corner of the stitched image and select the overlap area. Click Find Homography. The image is not fully aligned, but we are satisfied with this result. Even though it is not perfect, our focus is primarily in the center of the image. And this tree south will improve when we add the images in the mosaic left side. So let's continue. Load the next camera as before and look for sample 6. Move the picture to the left and adjust the overlap area. Checking the results, that looked pretty good. Okay, let's load the final camera. Find the sample 6 and adjust the overlap area. Adjust the homography window and look at the results. This area looks bad. Let's zoom in. Look at these holes right here. They look misaligned. The car in the back and the middle are also moved down. We will need to do some manual adjustment. Starting with the white translation, move the target up and try to align the hole. There it is. But look at the car back there. The target is not up. So let's adjust the vertical scale on the white translation once more, since we adjusted the scale and the hole misaligned again. Continue changing the scale and the translation until the hole and cars align properly. Now that everything is well aligned vertically, looking at the white car here, the target is moved to the left. So increase the horizontal translation to move it to the right and align it with the referenced image. Okay, the cars at the center look good now. Let's toggle the transparency to evaluate the stitching. Can you see this rotation on the sidewalk? It looks like we can solve it with a bit of Z rotation. Let's give it a try. That helps, but look at the gray car's tire. It moved. Let's adjust it with a scale. Now, there is still some movement in the sidewalk, but further adjustments may misalign the center of the overlap area. Zoom out to see the bigger picture. The overlap area is large, and we're having troubles of blurriness in the left side of the overlap region. We can leave the calibration as it is now, and solve this with cropping during the stitching process. Okay, we're ready to save the parameters, so go to File, Save, and save them in the results.json. Take a look at the file. In this case, the array consists of 5 objects, with the information of images and homographies. You can use this JSON directly with the RidgeRun Stitcher GStreamer element, with a pipeline like this one, and you will get a video like this. Awesome! Now you know how to use RidgeRun Stitcher Calibrator to determine the stitcher parameters for your panorama setup using images or video footage. Take a look at the last video of this series to learn how to calibrate 360 footage.